So we are going to do the second section of Chapter 2 today, which contains the numerical summary. In the first section of Chapter 2, we talked about organizing data using graphical summaries. Now we are moving on to the second one. We are organizing data using numerical summary. So when you say numerical summary, especially for quantitative data, the calculations are done for numerical data. So most of the numerical summaries are for quantitative variables, so discrete or continuous variables. But for qualitative data also, we can do certain numerical summaries. We'll come to that later. We will start with numerical summary for quantitative variables. There are two types of numerical summaries mainly. They're called the measure of central tendency, and the second one is the measure of variation. So central tendency, it's actually the measure of location, or the center of the measurements usually. Then the measure of variation, it gives you a summary or idea about how the data are distributed. Okay. So under the measure of central tendency, we have four main measurements: mean, median, mode, then quartiles and percentiles. The mean, you already know. Mean is, on the other hand, you use the word average. Average or the mean. If you take a data set, you can add them together and divide by the total. That's the average. And median is the midpoint of the ordered data. Mode is the most frequently occurring outcome. And then you have quartiles and percentiles. They will also give you an idea about the location of data. So we'll look at them one by one and see the calculations, and then try to compare them. Later we look at the measures of variation. We will talk about the range, standard deviation, variance, and depending on the quartiles and percentiles, we have also something called the interquartile range. So let's look at all these measurements in detail. Okay, so let's look at the measure of central tendency in detail. So the first one, mean or the average, as you all know, the mean of the data set is the sum of the observations divided by the number of observations. So you all know this calculation. You add all of them together. So that is the sum of xi. So each x will be your observation. Xi is the ith observation. So when you have the summation, I will go from 1 to n. N will be the sample size. You take that summation and then divide it by the sample size n. So that will give you the sample mean, usually denoted as x bar. The population mean is the mu, but usually with the calculations, what we deal with the sample. So we use the notation x bar. So here's an example. The defective items data, we are going to reuse this data again and again. So that is why I have the name defective items data. The quality control manager is keeping track of number of defective items produced in a process. So I have the data set, the number of defects for 2 weeks. So you have 14 observations here, right? You can see there are 14 observations. Okay, so take out your calculators and find the average of this data set. Okay, go ahead, do the calculation and find the total first. Sum of xi, I goes from 1 to 14, divided by 14. Right, so find the total, divide it by 14, you can get the average. You can't hear me? Can't you hear me? Can you hear me or not? I switched.
Can hear you, madam.
Okay, I stopped the sharing screen. I just got a message saying you cannot hear me. So I guess you can hear me, right? Okay, so I'll share the screen again. Okay. Can you all see and hear both?
Yes, madam.
Okay, right. So I think I got the answer for the total. It's 373. See, 373 is the total. When you divide it by 14, you get 26.642, right? Okay, any other answers? Is this correct? The sum is 373. When you divide it by 14, you get the mean or the average number of defects, 26.642. Okay, I guess this is not hard. Okay, you all know these calculations already. Okay, so that is the average. Yes. Do you have any questions? Okay, next is the median. Median of a data set is the midpoint of the ordered data. So you have to keep this, you have to make sure you do the ordering or the sorting first. Okay, be very, very careful. The first thing you have to do is, before you find the median of a data set, or that is the midpoint of the data set, you have to make sure your observations are sorted. Usually we arrange them in ascending order or increasing order. Okay, so the first step is to arrange your data in ascending order or increasing order. So the median of a data set is the midpoint of the ordered data or sorted data. Not just the midpoint. You have to order the data or arrange them in ascending order before you find the midpoint. Now, depending on the sample size, the way you calculate median, it is a little bit different. If the number of observations is odd, if n is odd, then the median will be the exact midpoint. Okay, you will have an exact value for the midpoint. But if the number of observations is even, then when you find the midpoint, okay, you do not have an exact value, but you'll have a number of observations to your left and to your right. Therefore, the median becomes the average of the two middle observations of your ordered data. Okay, so depending on whether the sample is odd or even, the way you calculate the median, it's going to be different. When the sample size is odd, the median will be the exact midpoint. But when the sample size is even, the median will be the average of the two middle observations. Okay. So let's go back to that same defective items data set. Okay, there are 14 observations, but you can see that they are not in order. Okay, they are not in order. Can you arrange this data so it is in ascending order, starting from minimum up to maximum? Okay, so that's the first step. Okay, so anybody who can do the ordering, let me know. Okay, so you can see the ordered data now. Yes. So thank you for the answers. So I have 19 up to 41. Okay, so we have 14 observations here. 14 is even. Right? So if you divide n by 2, you get 7. So you have 7 observations to your left-hand side. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 7 observations to the left. So this will be your upper half of the data. And this will be the other way around. The lower half of the data and the upper half of the data. Now in this example, both the middle two observations are the same. So therefore, the median becomes the average of these two anyway. It's the same, which is 25. Okay, so in this example, the median is the average of the two middle points, which is 25 and 25. Again, the answer will be 25. Okay. Okay, let's try another example. So I'll write down a data set. Now we'll use a odd number of observations. I'll give you an ordered data set so I can find the median very easily. Okay. So how many observations are there? How many observations are there? You can see there are 9 observations, right? There are 9 observations, which is odd. So if you divide it by 2, it will be 4.5. So which means you leave 4 observations to the left, 4 observations to the right. Now you have the exact midpoint 72. So 72 is your median. Okay, so I guess this is very clear to you, right? So the median is the main thing that you have to remember is you have to order the data set and then you can find the midpoint. Depending on the sample size, even or odd, you should be able to figure out the midpoint. Okay. The next comes the mode of the data set. Mode is the most frequently occurring outcome. Okay. That means if there is an observation that occurs repeatedly many times, then you call it the median. The mode. So if there is one observation that appears only once, and there can be some observation that appears twice, there can be other observation that appears 3 times, and so on. So anyhow, if you can find an observation that occurs many times repeatedly compared to the others, we call it the mode. Okay. So the mode is the most frequently occurring outcome or the observation. Okay. Now, what do you think about the mode? Is it unique? Can there be samples without a mode? What do you think? Okay, let's go back to the defective items data. Now, in this data set, there are 14 observations, and you can clearly see there is one observation that occurs many times. What is it? What is the observation that you see repeatedly many times compared to others? That is the value 25. Yes. How many times is it occurring? 1, 2, 3, 4, 5. 5 times. So the mode of this data set is 25. Mode is 25. The number of occurrence is 5. It appears 5 times. Okay. Now, can there be 2 modes for a data set? What do you think? Can there be many mods to a data set? Is it possible? Yes, it is possible, right? You can have a data set and there are two observations, both of them appears say 10 times. Okay, so that means it has two mods. Okay, maybe there are three mods. There can be observations that repeatedly occurs same number of times for their frequency. Then you'll end up with multiple mods. So for a given data set, you may end up with only one mod, that is the unimodal, two mods, bimodal, or more than that, that is the multimodal. Or sometimes you will end up with data sets where you cannot find a mod. That means all the observation appear only once, like the previous example, this one. The example I gave you to find the median with only 9 observations, you don't see any repetitions. So in this one, all the observations appear only once. Okay, so you end up with no specific mod. Okay, so you see that mod is not unique. That means you cannot say there's only one mod for a data set. Okay, you cannot say that because you may end up with no mod at all, maybe only one, two, or many. Now, can you see the difference between median and the mean with the mod? What do you think about the mean and the median? Can there be two averages for a data set? Can there be two midpoints for a data set? No, right? So the mean and the median are unique. There's only one and that is it. There will be one and only measurement. There will be one mean for a data set. There will be one median for a data set. No repetitions and always there is a one. Okay, so unless there's only one observation, then that observation will be the mean and the median also. Okay, so therefore, mod is behaving differently compared to mean and the median. Okay, is that clear to all of you? Right. So the difference from the mean and the median, mod is not unique and there can be many mods, and the mean and medians are unique, and that means there's only one value, given value for mean and median for a given data set. Okay, right. Now let's compare these three measurements for a data set. Okay, so you see in this example, two data sets, data set 1 and data set 2. These are the values of certain product measured in dollars. So you can forget about the unit of the measurement. So in the first data set, you see 10 observations. Okay, there are 13 observations, right? In the first data set, let's say N1 is 13. And the second data set, N2 is 10. Okay. Now you have to find the mean, median, and the mod of these two data sets, right? So the calculations are done for you. For data set 1 and data set 2, you see the averages. The first one 483.85, 474.0. Then the median, which is the midpoint of the data set. They are not in order, but if you can order the data set, you'll find that for the first, the data set 1, the median is 400. For the second one, it is 350. Then the mod is 300 for both because in the first data set, 300 appears how many times? 1, 2, 3, 4, 5, 6 times, right? And in the second data set, 300 appears 4 times. Okay, so those are that is the mod for both data sets. Okay. Now, since you have 3 measurements to get an idea about a data set, about its central tendency, okay, or the behavior of the center of the data set, to get an idea about the center of the data set, you have 3 measurements: mean, median, and the mod. Now, what do you think? Which one is the best? Is it the mean, is it the median, or is it the mod? What do you think? Which one is better? Any arguments on that? We can do it as a discussion. What do you think? Which one is better, or is there a better one? Or will that depend on the data set? What do you think? cannot hear you properly. Okay, so the problem is you cannot say one is better than the other one. Okay, usually we cannot say one is better than the other one. Depending on the behavior of the data, sometimes mean will be the best one, sometimes median, sometimes the mode. Sometimes both mean and median will be okay. Sometimes only mode will be okay. So it completely depends on the behavior of the data set. Okay. Now let's look at an example. I'll give you another example and see how the mean and the median behaves for two different data sets. So when you do a slight change to a data set, what will happen to the mean and the median? Okay. So here's an example. So I have, I'll start with a very small data set to explain it easily, right? So I have a data set, number of observations 7, okay? Number of observations 7. So here's my data set. I'll give it in ascending order, so it is easy. So my data set is 10, 11, 11 again, 13, 14, 20, 29. Okay, 7 observations. Right. For this small data set, can you find the mean and the median? Median, usually we use x tilde. I didn't mention it earlier, x bar and x tilde. So can you find the mean and the median for this small example? The mean, you have to add the values and find the average. The median, it's clearly visible. This is odd. This is 13. Okay, can someone find the mean of this data set? Yes. 15.42. Any other answers? $15.428. Okay, I guess that's correct. 15.428. Okay. So in this data set, the mean is 15.428 and the median is 13. Now what I'm going to do is I'm going to do a small change to this data set. Okay, I'm going to do a small change to this data set. Suppose when this data was recorded, 29 was mistakenly recorded as 92. Okay, a recording error. Now tell me what will happen to the mean and the median. Now calculate the new mean and the new median. You can clearly see that the median is not changed at all, right? The median will remain same. Now what will happen to the median? The mean. So what is the new mean? Okay, so you get new mean is 24.4. Any other answers? 24.42. Okay, so this is the new mean. Now compare your answers. The first one and the second one. Now what do you see? So at the end of the observations, one observation became a very large number, right? So compared to 29, 92, it's compared very a larger value. So what will happen to the mean? Mean also increased. And look at the difference, 15 to 24. Okay, almost 10 units, right? 24.4, almost, it's 9 units, almost 10. But the median, it remains same, no harm at all. What is the reason? Median is only the position. The median is only the position. So whatever happens in the end parts, the tails, the median is the midpoint and it is not going to change at all. Even you add a value to this data set, it will go one position to left, 13 and 14. What will be the average? 13.5. Again, a small deviation, just 0.5 difference, right? So the median is usually not affected by whatever happened to your data set in tails. Okay, in the endpoint, the left tail or the right tail, any difference, any behavior in those tails, the median is not affected at all because it's just a position, right? On the other hand, the mean is calculated by adding each and every data point. So any difference that you may make for the values of the data set, even in the middle or even in the endpoints, even in the tails or the middle, anywhere, if your data set is changed, the mean will be changed by a considerable value, considerable amount. Okay, so that is the difference between mean and the median. Whenever you have extreme observations in your data set, we call them outliers. Okay. Now look at this first data set, 10 to 29. All the values are within the range of 10 to 30, right? 10 to 30, they are close to each other. But as soon as you change the value 29 to 92, you see that there's a huge gap between 92 and the rest of the values. So 10 to 20, they are all gathered in between the 10 and 20, right? And then straight away it jumped to 92. Okay, there's a huge gap, about 70 points, right? So you can see that 92 is lying far away from the rest of the bunch of the data. Okay, so you can see that this is the rest of the data. 92, it's extreme value. Okay, or it is lying far away from the rest of the data. This can happen to both ends, maybe to the right side, maybe to the left side. So we call them outliers. Okay, outliers or extreme observations. Have you heard about this term anywhere else earlier? Outliers, extreme observations. So those are the observations which are far away from the rest of the data, which are uncommon observations, right? So whenever there are outliers in your data set, the median will not get affected. Median will not get affected because the outliers are in the far ends. Either it's the left tail, either it's the right tail. The median is just the midpoint. So whatever happens in the tail, median is not affected. The median will not affected by these extreme observations or outliers. On the other hand, the mean will be highly affected by these extreme observations or outliers. Now you can see that if there are outliers in your data set, mean is not going to be a good measure of central tendency. Okay, because it is biased. Okay, we say mean is biased to outliers. Okay, mean is biased to outliers. On the other hand, median is not. We say median is resistant to outliers. Okay, so therefore, if there are outliers or extreme observations in your data set, median will be a better measure of tendency compared to the mean. Okay, but if there are no extreme observations, then mean will be the best one. But if there are extreme observations, median will be the better option than the mean. Is that clear to all of you? You can see the difference, how these values are affected if there are outliers from this example very clearly. Okay. So let's talk about these outliers in detail. Okay, outliers or extreme observations. So you already know they are the observations which are lying far away from the rest of the data. Okay, so these are the observations. Lying far away from the rest of the data. So you can have outliers to the left or to the right. Now, what are the reasons for outliers? What are the reasons for outliers? Any idea? You can see one reason from this example already, recording errors. Okay, sometimes say 100 will be, say 10 will be recorded as 100, 1000, you know, mistypes can happen, right? So one reason is the recording errors. Yes, so one person gather the data, another person do the recording. So sometimes this can happen. And when you are going to analyze the data, you do not know whether that is the exact observation or whether it is an error, right? So if it is a recording error, you can correct it, okay? But sometimes outliers, they are the exact observations, exact extreme observations. There can be, right? There can be students in a class. All the other students got exam scores around 50 and 60, and there's one student who got full marks 100. Obviously, that's not recording error. That's the performance of that student, an extremely high performing student. Okay, so that person is an outlier, but you can't drop it. Okay, you can't drop that person or you can't change it. It's the exact value. So if there are extreme observations, outliers, but still if you have to keep them in the data set, you have to. You can't forget them, right? Some extreme observations due to measurement errors of the instruments, things like that, sometimes we drop them if they are not harming the analysis of your data, okay? Some extreme observations you can drop, okay? Can you drop outliers? This is another huge topic in statistics that you have to discuss separately. We usually do not drop outliers unless we know for sure that it is not going to harm our analysis or the objective of the study, right? So whenever you see outliers, usually outliers make problems. Your analysis, your results will be highly deviated when there are outliers. Whatever you want to explain will not be obtained because of the outliers. So they are really a headache sometimes. But some outliers you can drop by confirming it is okay to drop. There are statistical tests to check whether that outlier can be dropped or not from a data set. Okay, if it is okay, you can drop. If not, you have to keep them. And you have to handle the outliers properly and do the analysis. Okay. And there are statistical tests to check whether there are potential outliers in a data set. Okay, and then after identifying them, you have to decide again using test whether you can keep them or whether you have to drop them. Okay, it's another different area that you have to study thoroughly, right? But keep in mind, by just seeing an outlier in your data set, you cannot blindly drop it. Okay, you cannot drop it. You have to look at it in detail, whether it is an error, then correct it. If it is actual observation, is it harmful to keep it or is it you have to keep it? Okay, you have to study it before you do anything with your outlier. Okay. When you drop an outlier from the sample size, will it affect? Now it depends on the sample size. Okay. Now suppose your sample is about 700, 800 and one outlier. If you drop one outlier, your sample size will be decreased by 1. Okay, in that situation, it will not affect a lot. But if your sample size is about 20, 25, then dropping one observation, it will affect. Okay, so that is another thing that you have to check. Thank you for mentioning the sample size. Okay, whether you can drop the outlier or not, you have to think about the sample size also. So that is why I said you cannot just drop an outlier. If there is one in the data set, you have to study it properly before you do it. Okay, if it harms your analysis, you cannot drop it. You have to keep it. Okay. Right, so we'll come to outliers later when we draw the box plot at the end of the lesson. Okay. Right. Now let's compare the value of the mean and the median for a given data set. Right. You can see 3 different shapes. You already know them: the symmetric, right skewed, and left skewed. Right skewed is the positive skewness. We talked about them when we discussed the shape of the histograms last time. right? Positive skewness. Left skewed is the negative skewness. You can see how the mean and the median behaves. Okay, let's start with the symmetric. If your data set is symmetric, your mean and the median, they will be very, very close to each other. Maybe not exactly the same, but very, very close to each other. Okay, so mean and the median are very close in a symmetric data set. But if your data set is right skewed, you'll see that mean is larger than the median. The value of the mean is larger than the median. And if your data set is left skewed, mean will be less than the median. Now, how do you understand this? Mean always goes toward the longer tail. See, the longer tail is the right tail. So mean is always to the right compared to the median. In left skewed, longer tail is the left tail. Mean is going to the left, right? So remember that. Mean always goes toward the longer tail. Okay, so if you can remember that, you know how to place or where to place mean and median in a right and left skewed data. Okay, mean always goes toward the longer tail. So the positive skewed distributions mean will be larger, and negatively skewed distributions mean will be smaller compared to the median. Now by this information also, you can get an idea about the shape of the distribution. If you do not have a histogram drawn for your data set, by looking at the mean and the median, you can get a slight idea whether it is symmetric or whether it is skewed. Okay, right. Now we come to the next set, the quartiles and the percentiles. So we'll start with the quartiles first. You have already learned one quartile, which is the second quartile. The second quartile is the median of the data set, right? So this is how you explain the quartiles. If you have your ordered data, see the increased order. So if you have your ordered data set, the exact midpoint will be your quartile, the median, second quartile. Then the midpoint of the first part will be your first quartile. Midpoint of the upper half will be your third quartile. Okay, so which means your whole data set will be divided into 1/4. That's why they are called the quartiles. You divide the whole data set into exact 4 parts. Okay, so each of them will contain 25% of your data, right? So Q1 or first quartile, usually denoted as Q1, the first quartile contains the lowest 25% of the data. In between Q1 and Q2, you have the next 25% of the data. So likewise, you can see it. And the midpoint, median, at the median you have to the left, the lower 50% of data, to the right, upper 50% of data. What about Q3? At Q3, you have, to the left of Q3, you have the lower 75% of data, and then to the up, you have upper 25% of data. Okay, so you can clearly see that from quartiles, you divide the whole ordered data set into exact 4 parts, each having 25% of the data. Okay, so the third quartile is the Q3, that is the midpoint of the upper half of the data set. So this is easy to calculate, right? Okay, so let's try to find the quartiles of this given data set. You see the measurements of amount of solar radiation in a greenhouse. Okay, so how many observations are there? 12, 15, 18, 21, 24, 26, right? There are 26 observations, right? And it is already ordered for you, so you don't have to spend time on sorting it. You can see the lowest 6.3 up to the highest 13.1. Okay, now start and divide the data set. First divide it into half, find the median Q2, and then look at the upper half and divide it into 2 and find Q1, and go to the upper half, divide it into 2 and find the Q3. Can you do that? Okay. So 26 divided by 2, you get 13, right? Exactly 13. Is this ordered? Oh, there is one. It should be 8.5. Okay. Thank you for pointing out. This 5.5, it is actually 8.5. Okay. Not 5.5. Okay. Right. Any other missprints? I guess no. Okay. Right. So where's 13? Let's do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So here's the midpoint. So you have 13 to the left, 13 to the right. Okay. So what is the median? Or Q2, second quartile. Have to average the middle two observations. So 10.4 plus 10.6 divided by 2. Okay, so what do you get? 21 divided by 2, 10.5. So 10.5 is the median. Okay. Now remember, you do not include median when you find the quartiles, the Q1 and the Q3. Okay, 10.5, it's there, don't touch it. Okay. Now the first half is 13, odd number of observations. When you divide it by 2, you get 6.5. So 6 to the left, 6 to the right, you'll get exact midpoint. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So you get 8.9. That is our first quartile. Okay. Here, 8.9 is the first quartile. Okay. What about the third quartile? Here's the midpoint. So our upper half starting from 10.6. 1, 2, 3, 4, 5, 6. From the upper corner, 1, 2, 3, 4, 5, 6. So what is the third quartile? 11.2. So this is how you find Q1, Q2, and Q3. Always start from the median and then work for Q1 and Q3. Okay. Any question from this one? Shall we try another one? Let's try another one. Another small data set. Okay. Okay, try this one. Right. Can you find the quartiles? Start from the median, then first quartile and the third quartile. It is already ordered, so you can start now. Sample size is now 11. Okay, tell me what is the median first? Yes, what is the median? Median is 105. Thank you. So you have 1, 2, 3, 4, 5 to the left, 1, 2, 3, 4, 5 to the right. So exact midpoint 105 is the median or the second quartile. Okay, so get the other answers also, Q1 and Q3. Let's find it. Now, do you include this one to your upper and lower half? 105, no. So you don't touch it. Okay, so after you find the median, leave it there. So here's your here's your lower part from 92 up to 72. Even in this one, the previous one, you find the median 10.5. You do not touch it after that, right? So 1.5, you leave it there. So when you find Q1, you look at the upper half starting from 90. So sorry, the lower part starting from 92. So there are 5 observations. So the midpoint will be 85. Very easy. And again, the upper half start from 110. Okay, so the mid part 170. So those are your quartiles, right? Those are the quartiles. Okay, thank you for the answers. So is it clear to all of you? How do you find the median and then the quartiles? Okay, whether it is odd or even number of observations, you know now how to find it. Okay. Now again, think about the outliers. Suppose you have 2 different values. This 125 is, let's say, 195. Will that affect your quartiles? Or this 72 is 12. Okay, if you change this 72 to 12 and this 125 to 195, what will happen to your quartiles? Will there be any change? No. Right? These are just the positions. So whatever happens in the tails, they are not visible to the positions. It will still be 85, 105, and 170. But if you calculate the mean for this original data set and this changed data set, you'll see the mean is going to be very, very different. Okay, so that is why I say mean is highly affected by outliers, but median not. Okay. So is that clear to all of you, the quartiles? Any questions so far? Right. In the same manner, you can find the percentiles. Okay. The percentiles, that is where you give or you divide your data into percentages. Okay. I'll show it using an example. Suppose after you draw a histogram or something, your data set looks like this. Okay. So this is the ordered distribution of the ordered data. Okay. The ordered data. Now, if you can find a point or an observation, okay, so this observation, let's say it is just xp, and if you can find the percentage to the left of that point, okay, the percentage of observations to the left of that point, we call it is the p percentile. Okay, so as an example, if you can find an observation where 80% of data falling left to it and the rest 20% in the upper corner, you call this the 80th percentile. Okay, so this is the 80th percentile. Again, this is the ordered data. So for ordered data, if you can find a point so that 80% of data fall into the left of it, you call that point the 80th percentile. Okay. Now tell me this one. In your observations, you can find observations so that there are 90% of observations to the left of it. So what is this? What is this point? What do you call it? What is the percentile? That's the 90th percentile. So what is the percentage to the right then? The rest should be 10%. So altogether you have all 100% of data. Is that clear? What about this one? So you have your data set. To the right of the distribution, you have 25%. So what is this percentile? You have 25% to the upper corner. What is this percentile? Yes, that is the 75th percentile. Very good, because if you have 25% to the right, the rest 75% to the left. So always you name the left percentile, okay, the left percentage. So this is the 75th percentile. Can you give me another name for 75th percentile? Something that you have learned a little bit ago? Another name for 75th percentile? Anybody? Another name for 75th percentile. That is the third quartile. Very good. So this is actually Q3, right? So which means, tell me, what is the median? What is the percentile for the median? Median is the exact midpoint, 50% to the right, 50% to the left. So what is the median? Median is the 50th percentile. Now you know 3 different names for the same calculation. The median is Q2 and it is also X50 or 50th percentile, right? 50th percentile. So what is Q1? Q1 is 25th percentile. We shall use tilde. And Q3 is the 75th percentile. Okay? Right. Okay. So those are the measurements of central tendency that you can get an idea about the center of your data set. Okay. So now we move on to the next set. Those are the measures of variability or measures of variation. Right. Okay. Now look at these 2 teams. Right. So you can see their heights. The first one in feet and then the same value measurement in inches. So these are in feet and inches, both feet and inches, 6 feet 0 inches, 6 feet 1 inch and so on. But if you convert it, 1 feet is 12 inches. So this is 72 inches, 73 and so on. Okay. Now what can you see from these 2 teams? So let's try to do some calculations. Okay. If you look at the team 1 and team 2, the minimum or the tallest and the shortest players, right? So if you look at the team 1, the shortest player is the one having 72 inches, right? See, the shortest one is the one having 72 inches and the tallest is having 78 inches, okay? And then we have the next team, the shortest is 67 inches and the tallest 84 inches. Now what do you see there? If you compare team 1 and team 2, so you can say these are the minimum and the maximum, right? Min and the max. If you look at the minimum and the maximum of these 2 data sets, you can see that for team 2, minimum is smaller compared to team 1 and maximum is larger compared to team 2. So if we can find the distance between minimum and the maximum, we call it the range. Okay, so the range of the data set is the maximum minus minimum. So if you look at these 2 teams, you can find the range of team 1 and team 2. What is the range of team 1? Let's find it. The range is, let's say range 1. That will be 78 minus 72, which is 6 inches. What is the range of team 2? Maximum minus minimum, 84 minus 67. What is the answer? 7. Let's find the minimum. Yes, what is the range? Range of the second team? 84 minus 67 is 17, right? So you can clearly see that the range is larger for the second team compared to the first team. What does that mean? The heights of the players of the first team are very close to each other. Okay, the range is short. That means they are gathered very close to each other. On the other hand, team 2, the heights are distributed amongst 17 points, right? So it is the values are distributed very far away from each other, okay, for a larger span. So that is the variance. So the variation of team 2 is bigger compared to the variation of the first team. Can you see that? Right? So if you draw a dot plot to this for these two teams, you will see that, right? So you'll see that 72 and 68 somewhere here, 72 and 78, sorry, and the players are here. And then the other team, it's 67 and 84. And their heights are, see, the 5 players will be distributed in a larger span. See, you can see it. So the team 2 is distributed widely, but this one is very close. Team 1 is, the heights are very close to each other. Okay, I hope you can see the difference between the variations. So the variability is high for team 2, and the variability is low for team 1. Can you see that? So this is high variability. This is low variability. Right, so range will give you an idea about the how these data points are varying, okay, how they are distributed. Okay, now what do you think about this calculation, minimum and the maximum? When you find the range, you do the calculation by using minimum and the maximum only. Okay, so that is the largest and the smallest. You just get the difference of this maximum and the minimum. But you are not going to look at whatever the values you have in between, right? So all the other values, this 73, 76, this 72 and the other values, you are not touching them at all. You don't actually care what the values are inside minimum and the maximum when you find the range. They can be anywhere. So therefore, the range will not give you the exact information about the variation of the data. Okay? The range is calculated using minimum and the maximum, and whatever the values in between those two values are not touched. They are not used. The information that are available in observations in between minimum and the maximum are not used to calculate the range. Therefore, not all the information are used when you calculate the range. But there is a better measurement which is called the standard deviation that will use each and every observation of your data set when you calculate the variability. Okay. Therefore, a better measurement is a standard deviation. Okay. So compared to the range, standard deviation is a better measurement because it uses information of all the observations in your data set. So this is how you calculate the standard deviation. Can you see this? So let's look at it. So you have xi, these are the observations, xi. You take each and every observation and get the difference from the mean, see x bar. So it uses the mean also. Okay, so first you calculate the mean or the average of the data. Then you find the difference between each and every data point to the mean, xi minus x bar. Okay, so any observation to the left of x bar will give you a negative value. Any observation to the right of x bar will give you positive values. Now, in order to get rid of this sign, you square it. So all the negative values will be positive. So you square the deviation, we call this the deviation. Okay, so xi minus x bar, we call this the deviation. After you find the deviation, you square it. So you get the squared deviation, add them together, divide by n minus 1, get the square root. You call it the standard deviation. Okay. You don't have to memorize this equation. We are not using it, the hand calculations. You can use Excel or even a statistical software to calculate the standard deviations. when your data set is large, doing hand calculation, it is not recommended. Okay, so we use tools to calculate the standard deviation, but you should know how it is done. Okay, so if I explain it using a small graph. Okay, so here are my observations, x1, x2, x3, up to xn, right? Suppose you have mean somewhere here, x bar. Okay, now remember, mean is the balance point. Mean is called the balance point. That means if you put a small bar on a certain fulcrum, you know the fulcrum. Okay, so like a seesaw, it goes up and down. Where this bar will balance, that is called the mean, right? So mean is the balance point of a data set. Now what you do in the deviation is you find the difference to the mean for each and every data set. So x bar minus x4 minus x bar, x3 minus x bar, x2 minus x bar, and so on. Okay, so you find this deviation for each and every observation, right? Okay, so if you find the deviations of all the data sets, xi minus x bar, and add them together, what do you think? What will be the value? If you find the deviations of each and every observation with the mean and add them together, what do you think? What will be the value without squaring it? What do you think? Any idea? What will be the sum of the deviations? Anybody who can answer the question? Remember, mean is the balance point. Who can answer that question? What will be the sum of the deviations? No idea? So that will be 0 because it's a balance point. So you get the negative values, positive values here, and they will cancel out because mean is the balance point. So if you sum up the deviations, they will be 0. But when you square, you get rid of the sign. So you get a certain value for xi minus x bar square and then add them together. So you'll get a value. Someone has the microphone on and it's disturbing. Please, can you switch off it? RAD15, can you please switch off your microphone? It's kind of disturbing. Okay, thank you. And then after you find the square deviations, the sum of it, you divide by n minus 1. So anybody who got the question, why we divide by n minus 1, not n? Why is that? Now remember, this is the sample standard deviation. Okay. If it is the population standard deviation, we divide by the population size capital N. Okay. The population standard deviation will be calculated as xi minus mu, the population mean square, divided by population size n square root. This is the population standard deviation. But there is a certain feature in estimates, you know, sample standard deviation is the estimate for the population standard deviation. There is a property called unbiasedness. In order to achieve that, we have to divide by n minus 1. Okay, that is it has some theoretical aspect. So we are not going to talk about them in detail, but this is the equation we use. Okay, so that is the sample standard deviation. The difference from range is the range uses only the minimum and the maximum, but the standard deviation use each and every data point in your data set and how it relates to the mean. Okay, and that is how you calculate the standard deviation. And there's a computational formula to calculate standard deviation if you do it by hand. Okay, but again, you don't have to memorize it. Okay, right. So here's an example we'll do a small comparison using mean and the standard deviations of these data sets. In data set 1, both of them have the same sample size. There are 10 observations, right? The first one and the second one, both of them have the same mean, 50, right? So if you average these observations, you'll end up with the same mean, 50. But if you find the standard deviation, the first one is 7.4 and the next one is 14.2. What does that mean? The second data set has higher deviation or higher variance compared to the first data set, right? And you can see it by looking at the data also, right? See, the minimum of the second data set is 20 and the maximum is 70. But the minimum of data set 1 is 41 and 66. So the values are gathered around 40 and 66. On the other hand, second data set data is spanned from 20 to 70. So that span is bigger compared to the first one. So you see that variation. Okay. So there can be data sets, they have the same mean, but they have different standard deviation. That means different variability. Okay. So if you compare a few of these variations, you can have something like this. Okay. So suppose I'll try to draw it in the same graph. If you draw the histogram, what will happen, right? So you'll get a nice symmetric distribution. Let's say variables X and Y, right? So this is the distribution of X. Here's the mean of X, okay? X bar. And it has a certain standard deviation. And then when you draw the Y, it has the same mean, but its distribution is like this. Now, what do you think? Same Y bar and X bar are same. Now, what do you think? What do you see here? The means are same, but X has a larger variability. See, the bell is thick, fat. But for Y, the bell is thick, thin, right? It's very thin. So the variability of Y is smaller compared to variability of X. Okay, so variability of X is larger compared to the variability of Y. Same mean. Okay, it can have that. Now look at this one. What do you think here? Now you can see it's approximately same in the shape and the fatness. So the variability is same. But here's the mean of X. Here's the mean of Y. Okay. So Y has a larger mean compared to X, but both of them have the same variability. Okay. So that is also possible. And there can be some distributions. Here's X. And there's Y. What do you see here? Okay. For Y, mean is larger than X and variability is also smaller. Okay. Very small variability. On the other hand, X has higher variability, mean is smaller. Okay, so that is how you can explain the variation of a data set. Okay, so simply variability or deviation is whenever the data points are close to the mean, that is the balance point. Whenever all the observations are close to the mean, you get less variability. When the observations are lying far, far away from the mean, you get higher variability. So let's note it down. when observations are closer to mean, you get less variability. When observations are far away from mean, you get high variability. Okay, right. Any questions so far? No questions? Okay. Then you have the other measurement, which is the variance. So there's nothing special about it. Variance is the square of the standard deviation. Okay, so your standard deviation is the square root of xi minus x bar square n minus 1. So when you remove this square root, you get the variance. So a square is simply sum of xi minus x bar square divided by n minus 1. Okay, the variance is a square. Okay, that means without the square root. The variance and standard deviations, they are always positive. Okay, so remember that standard deviation and variance, they are always positive. You cannot get a negative value for the variance. Okay, because when you take the square root, you always get the plus 1. You get plus or minus square root, but with the standard deviation, you always get the plus 1. Variance is the square, so obviously it is going to be positive. So when you do a calculation, if you end up with a negative value for variance, that means it's wrong. Okay, your calculation is wrong. Variance is never negative. Okay, it is always a positive value. Same for the standard deviation. Right. So we talked about the range, standard deviation, and its square is the variance. The last one is the interquartile range. Okay, so you already know the quartiles. The interquartile range of IQR is the difference from Q3 and Q1. So which is very same to the range. The range is the maximum minus minimum. So similar to that, IQR is the difference between the third quartile and the first quartile. Now you can see the difference, or you can get an hint about the behavior of range and interquartile range. What is that? When there are outliers, the minimum and the maximum, okay, they will be the outliers actually, right? So your range becomes very, very large. But your Q1 and Q3, they are not affected by outliers. Okay, so when there are outliers, IQR is better than the range. Can you see that? Range is the min and the max. If min and max are exactly outliers, your range is going to be a huge value and it is misleading. But the IQR, Q3 and Q1 will remain the same, right? So interquartile range is a better measurement of variability if you have outliers rather than the range. Is that understandable to all of you? I hope so, right? Okay. Let's try to find the IQR of the solar radiation data. You already have Q1 and Q3. Can you remember them? For the solar radiation data, what was the quartiles, Q3 and Q1? Let's go back and check it. Okay, so Q1 is 8.9 and Q3 is 11.2. So can you find? Okay, so can you find IQR? Okay, very easy. (8.9 minus 11.2), which is 2.5. 3. Yes. Okay. So what is the range? X minus. We can find it. Okay. So I'm not going to do any calculations with the standard deviation because it takes a lot of time and usually you don't do it, but I'll show you how to do it when you do lab practicals. Okay. Even using Excel, you can try. They have the options or the functions already available, so you don't have to do any hand calculations. Okay. Right. So we talked about the measure of central tendency and then the measure of variability. The last topic that we have to cover is the box plot or the 5-number summary. Okay, the box plot or the 5-number summary is a graphical representation that uses the measures of central tendency, and that will give you a very nice idea about the distribution of a certain data set. Okay, the box plot, or when you see the name 5-number summary, it contains 5 values. Okay, so this box plot will give you, or it is drawn using 5 values. What are those 5 values? Minimum, which is not an outlier. Q1, Q2, and Q3, the quartiles. And then the last one, the maximum, which is not an outlier. Okay, so I have to be careful. They are not exact minimum and the maximum. The minimum and the maximum, which are not outliers. And then the quartiles. Okay. So which means when you have a set of observations for a data set, if you want to draw the box plot, you have to calculate these 5 values first. You know how to calculate the quartiles, Q1, Q2, Q3, you know how to do that. Order it, divide the data, and you know how to find it. Now, how do you find the minimum and the maximum, which are not outliers? There should be a way to do that, right? So we have to learn a way to identify potential outliers, right? So this, the one we are going to learn here, it's called the 1.5 times IQR criteria. Okay, 1.5 times IQR criteria. Right? So here what we do is we are going to find a lower limit and an upper limit for potential outliers. Lower limit and upper limit for a potential outliers. Okay, so how do you find it is after you find Q1, Q2, and Q3, you can find the IQR easily. Okay, you can find the IQR easily. And then what do? Is you get the IQR and multiply it by the value 1.5. Okay, you find the value 1.5 times IQR. Then you subtract it from the first quartile. That will give you the lower limit for potential outliers. Okay, you get 1.5 times IQR and subtract that value from your first quartile. That will give you the lower limit for your potential outliers. The other one is you take the 1.5 times IQR and add that value to your third quartile. That will give you the upper limit for outliers. So this is how you do it. You have your Q3 somewhere, sorry, Q2 somewhere, you have Q1 and Q3 somewhere. Okay, like this. You can find the IQR multiplied by 1.5 times IQR. Okay, and then you add, you add Q3 plus 1.5 times IQR. You get a value which is greater than Q3, right? So something somewhere here. So this is the upper limit for outliers, which means any value beyond this point, they are going to be outliers. Okay. Now you do the same for the left-hand side. You get Q1 and subtract 1.5 times IQR. Right? So you will find this value somewhere here. So any value beyond this point, they are outliers. They are going to be outliers. Is that clear? Right? So your minimum and maximum can be somewhere. It may be in this outlier range or not, right? We don't know. So when you draw the box plot, you have to find the minimum and the maximum, which are not outliers. Okay, so that is how you draw the box plot. Okay, we'll come to that after we do some calculations, right? But this is how you find the potential outliers. Okay, so you have the boundary for outliers, the upper bound and the lower bound, right? Okay, now let's see how we can construct the box plot. First, you determine the quartiles. You know how to do that now. You have to find the potential outliers. You know how to do that now using 1.5 times IQR criteria. Then you draw a horizontal axis, that is your number line, right? And then you mark the axis, the quartiles. You mark this axis with your 3 quartiles. Okay, and then connect these quartiles to make a box. Then connect the box to the adjacent value with the line. Okay, so you make the box, okay? And then if there are potential outliers, you draw it with an asterisk. So your final box plot will look like this, okay? So here's your number line. You have the median, Q1 and Q3. You draw the box covering the quartiles, right? Then you draw the line. This is minimum, which is not an outlier. And then you'll find the maximum, this is the max, right? Max, which is not an outlier, and this is the minimum, which is not an outlier. If there are outliers, you have to mark them using asterisks. If there are, maybe there are, maybe there are not. So your box plot will look like this, right? Now, depending on the range of your data, sometimes your box will be very fat, sometimes it will be very lengthy. So you call this, so this is the box, and these are called the whiskers, right? These are called the whiskers. So sometimes this is called box and whisker plot. So this, you know, the whiskers, like your cats and dogs, we have the whiskers besides their jaws. Okay, so that's why they're called the whiskers. Sometimes the whiskers are very lengthy, sometimes the whiskers are very short. Okay, sometimes the box is symmetric, sometimes it's positive skewed, negative skewed. So you can have all these shapes from the box plot also. Okay, right. So let's draw a box plot for this survival data. So this is a new data set. Right. How many observations are there? You can see there are 11 observations, right? 11 observations. Okay, so let's try to draw the box plot for this one, following all the steps. Okay, so if you want to do it yourself, you can follow me, right? So this is n equals 11. So first, let's find the midpoint. That is the median. 1, 2, 3, 4, 5 to the left. 1, 2, 3, 4, 5 to the right. So here's my Q2. Very easily, you can find Q1 and Q3. Okay. So what is the next step? You have to find the IQR. 25 minus 14, which is 11. Sorry, 9. Right? Which is 9. So what is 1.5 times IQR? 1.5 times 9. So what is the answer? 13.5. Okay. Now let's find the lower bound or the lower limit for outliers. What is the lower limit? Q1 minus 1.5 times IQR. Okay, let me know if I'm making any mistake, okay? So what is it? 14 minus 13.5. Okay, what is it? 0.5. So do you see any value beyond 0.5? No, right? So the minimum is 2. So the minimum, which is not an outlier, is 2. Can you see that? Right? Okay, then let's find the upper bound for outliers. So upper limit 4 outliers. That will be Q3 plus 1.5 times IQR. That is 25 plus 13.5. 25 plus 13.5. What is the answer? 38.5. Do you see any outliers? Do you see any outliers to the right? So the upper limit for outlier is 38.5. Do you see any value beyond that point? Yes, you see 41. Right? 41 is bigger than 38.5. So which means 41 is a potential. We use the word potential outliers. Okay, just not the outliers, because this criteria is just one. 1.5 times IQR criteria is only one criteria that will identify outliers. There are many other criteria used by different textbook, different softwares. So if you use another criteria, maybe 41 is not a potential outlier. Okay, we don't know. So therefore, we always use potential, the word potential outliers. Okay. Right. Now, how do you draw the box plot? You have Q2, Q3, and Q1. So no problem. So what is the minimum which is not an outlier? Your 5-number summary, you need minimum which is not an outlier. What is the value? What is the minimum which is not an outlier in this data set? You don't see any outliers to the left, therefore the two minimum will be the same value, right? So there are no confusions. 2 is the minimum, and which is not an outlier, again it is the 2. What about the other side? What is the max which is not an outlier? What is the maximum which is not an outlier? It should be 26. Very good. Now remember, it is not 38.5, okay? This is the limit that we calculated. This is the limit. But to draw the box plot, you need the max and min, which are not outliers. So 26 is the maximum, which is not an outlier, because 41 is outlier. You drop it. Now you have all 5 numbers to draw the box plot. Try to draw it in approximate scale. We have the values from 2 up to 41, right? Okay, so let's see. 5, 10, 15, 20, 25. Right. Start with the median, which is 19, somewhere here. Q1 and Q3, 14 and 25. 14, 25. Let's draw the box. Sorry, my box is not nice, but you can draw it nicely. You can see that the difference from Q1 to Q3, Q1 to Q2 is 5, and Q2 to Q3 is larger than that, right? 19 to 25 is 6 points, and this is 5 points. So you see the difference, or make sure the upper box is bigger than the lower box. Then you have to draw the whiskers minimum, which is not an outlier. It goes all the way up to 2 somewhere here. And then max, which is not outlier, is 26 somewhere here. And finally, you have to mark the outlier. So 40 will be somewhere over here. So that's all. That's your box plot. Is this clear to all of you? Any questions? If you follow the steps one by one correctly, without any errors in calculations, you will end up with a nice and correct box plot. Okay. Right. Okay. So similar to the other graphs, you can interpret your box plot. Okay. What are the things that you can say? The shape. So usually If you end up with nice symmetric box with viscous also symmetric, you can say that the data set is a symmetric data. Sometimes you'll end up with, usually we look at the box to get an idea about the skewness, something like this. So here's the median, the quartiles, and this something like this. So this is positive skewness. And in the similar manner, you can end up with the negative skewness of the data. Okay. So sometimes you may end up with outliers in both sides, only one side, or maybe none. So you can, when you interpret the box plot, always after you draw a graph, you have to say something about it, interpret it. Okay, that is very important in any graph, pie chart, histogram, dot plot, stem and leaf, box plot. After you draw it, try to write 2 or 3 lines about your graph. That's called the interpretation. Okay, because anyone can get a graph by clicking a button, but as statisticians, as students who know statistics, you should be able to say something about the graph. What are the information that you can extract? That is the interpretation of the graph. So say something about your box plot. Okay, whether it is symmetric, whether it is skewed, whether there are outliers, any important behaviors that you can see. So mention them. Okay, right. The nice thing about box plot is you can use it to compare different groups. We call it side-by-side box plots. Okay, say, for example, think about those 2 teams. The players, can you remember we were talking about the deviation of the heights of 2 different teams, comparing heights of 2 football teams. Right? So if you draw the box plot on the same scale, same number line, you'll end up with something like this. So the first group, can you remember, it had a very low variation, right? Something like this. And then for the second team, it has a higher variation like this. The box plot will look like this, both symmetric, let's say. So what you can say, you can easily compare the 2 teams. You can very easily see the team 1 and team 2. Team 1 has less variation than team 2. Both are symmetric distributions. So likewise, okay, you can mention it. Sometimes you have to use the box plot to compare the gender distributions, right? So if you draw the, let's say, the weight distribution of females somewhere here and the males somewhere here overlapping, right? Outliers, right? Something like this, right? Weight or height. So by using side-by-side box plots, you can easily compare groups, okay? And these are, you know, the box is the middle 50%, exact middle 50%, Q1 and Q3. So you can easily compare where these observations are lying, right? The upper 25% of observations are below than the lower 25% of the other group, something like that. You can easily mention. And see the medians. The medians are very different. For males, the median is very high compared to the median of the females. Right? So likewise, you can compare things very easily using side-by-side box plot. Not only 2 groups, 3, 4, 5, many groups. You can do it. Okay. So box plot is a very nice graph that you can use to do the comparison. Okay. I was thinking about doing a group work, but it's now it's 3:15. Now we don't have much time, but you can try this one. The solar radiation data set, you already have the values, the quartiles for this one. Try to find the limits for the outliers and draw the box plot and try to interpret it. Okay. So as a homework, try to draw the box plot for the solar radiation data. Okay. Right. Any questions so far? So only thing left from this section is the numerical summary for qualitative data. That's about calculating percentages. I'll discuss it in our next class. Okay, and hopefully we'll be able to start the third chapter in next class. Okay, any other question? No questions? Okay, so let's finish the class for today. And I hope you have understood the calculations and try to, there are several examples we did, and you can reuse those examples and try to do different other calculations reusing this data. And if you have any question, feel free to contact me.